This video will cover two examples of using interrupts in the ATmega 328. The first example uses the timer interrupt, and the second example uses what are called external interrupts. Starting off, the first example, our goal is to use timer 0 in normal mode in order to generate a 25 kilohertz square wave on port D pin 1 or PD1. And our machine clock frequency is 8 megahertz. So we know we have a square wave at a certain frequency, and we need to figure out what delay that requires. So here's the output of our pin. It's high and low for equal amounts of time, and the total time here is the period for the wave. And the period is defined as the inverse of the frequency, which is 1 over 25 kilohertz, which is 40 microseconds. So this here is 40 microseconds. And that means that the delay from our timer is 20 microseconds, because we'll turn on the pin, wait 20 microseconds and turn it off, and wait 20 microseconds and turn it back on. So delay is 20 microseconds. Now with an 8 megahertz clock and an 8-bit counter, we can get a 32 microsecond delay with no prescaler. So in this example, we don't need a prescaler. So the number of bits or number of increments is just delay divided by T1, which is 20 times 10 to the minus 6 over 0.125 times 10 to the minus 6, which is 20 times 8, so 160. And since we're in normal mode, we find out to preload the counter, TCNT 0 is 256 minus N, which is 96. Now, we need to figure out the timer counter control register values. For this microcontroller, there are more than 8 bits to control the timer counter. So that's why there are 2 timer counter control registers. They just had to spread those bits over 2 different registers. And so we'll refer to the data sheet to find out what we need for the WGM and CS bits. So here we have the section of the data sheet for timer counter 0. And we can come down to the register description and the timer counter control register. So here's TCCR-A or TCCR-0A. So this should be TCCR-0A, TCCR-0B. We need to figure out what the WGM bits need to be. Here's our table for their values. And for normal mode, we need them all to be zeros. So WGM, and these are called 02 through 00. We got 02, 01, and 00. The first number is which counter, and the second number is which bit. So WGM 02 through 00 equals 0. My camera froze. Okay. So WGM 00. And now the CS bits, those are in timer counter control register B. The CS bits with no prescaling, we need 001. So CS 02 through 00, and that's equal to 0, 0, 1. Now we know the values to go into the timer counter control registers, but we need to know where those bits are in the registers. So here's TCCR0A. All these bits we're leaving as zeros. These reserve bits need to stay 0, and here's our WGM bits. For normal mode, they're all zeros, so TCCR0A is just 0. And now control register B. Oops. These will leave as zeros. The reserve ones have to stay 0. WGM, this bit is 0, and the clock selection bits of 001. So TCCR0B is just 1, because it's 7 zeros and a 1 in the least significant bit. And the camera froze again. So we also need to look at the timer mask register. Maybe if I just disconnect it now, it won't freeze again. So the timer mask register for timer 0. This is how we enable the different interrupts. I'm sorry, timer interrupt mask register. This is how we enable the different interrupts for timer 0. So we've got the output compare interrupt B, output compare interrupt A, and timer overflow interrupt. And we want to enable the timer overflow interrupt since we're using this in normal mode. So the register TIMSK0 is going to be 7 zeros and a 1 in the least significant bit. So these all remain 0. We don't need the output compare interrupt, so these are zeros, but we do want the timer overflow interrupt, so we'll set that to a 1, and that will enable the overflow interrupt for timer 0. So TIMSK0 is also equal to 1. And so this enables overflow interrupt. All right. So now we know what registers we need to set up. We can go ahead and create the code. We need to be sure to include io.h because we're going to want to use the ports and DDRB in those registers, and also include interrupt.h. And go ahead and find main. Well, let's start by setting up the IO pin. We need pin 1 of port D to be an output, so we'll write a 1 to that bit. And then set up the timer. So now we've got it in normal mode with no prescaler. And preload the counter with our value to give us a 20 microsecond delay. So these 3 lines were for setting up the timer, and now we'll enable the interrupt. But it still won't go through yet because we haven't enabled the global interrupts, or we haven't set the I bit in the status register. So we use the function SEI to enable global interrupts. And that's it. So now we've got our timer going. Whenever it overflows, we will generate an interrupt. And so we can just create our infinite while loop, while one, and it's just going to stay on this line forever. And then just for good form, we'll put this return at the end of main. And now we need to define our interrupt service routine. So now that we've finished main, go ahead and define the ISR for, and the vector name is timer 0 OVF underscore effect. And the only thing this does is toggles port D pin 1. So D is equal to whatever it was before, exclusive OR with 1 left shifted 1. And you can use this exclusive OR with a 1 to toggle a value. And that's all that goes in the ISR. And to find out this name for an interrupt, you can look again in the data sheet. So over here we have interrupts, and then all the vectors for the different microcontrollers that are covered by this data sheet. So we'll come to the 328, and here's the name of the source, and the vector name is just the name of the source with the spaces replaced by underscores, and then lowercase vect afterwards. So timer 0 overflow, timer counter 0 overflow. The vector name is timer 0 underscore OVF underscore vect. And another thing that this table also shows besides the vector names is the priority. So if, for example, timer 2 overflows on the same cycle that timer 0 overflows, and you have both of those interrupts enabled, you're going to handle the timer counter 2 overflow first because it has higher priority. So that was our example for using a timer interrupt. Now we can have a little intermission and an example for external interrupts. So an external interrupt, you can see here, they have the highest priority. An external interrupt is generated by a signal on one of these pins. So you can see here that port D pin 2 and port D pin 3, they have the functions INT0 and INT1. So these are the 2 pins that are used for external interrupts. And so if something happens on one of these pins, it can generate an interrupt also. And that's what we'll use in this example. So coming back down to the interrupt vector table, we see that the vector names are going to be INT0 underscore vect and INT1 underscore vect. So in this example, we want to, well, let me talk a little bit more about the interrupts and how they work. So let me draw the hypothetical voltage on pin INT0. So say it starts out high voltage and then drops to low voltage and then stays there for a while and comes back up. Well, interrupts can be generated in different ways depending on the sense control mode that we set up. So we can generate an interrupt whenever the pin is at low voltage. So as long as this pin is at low voltage, it's going to be generating interrupts. So that's the first of the 4 sense control modes. Low level, and then logical change. So whenever the pin goes from high to low, that would generate an interrupt because that's a logical change. Or when it goes from low to high, that would also generate an interrupt if we have the external interrupt set up for the sense control for logical change. And then the third way is falling edge. In this case, an interrupt would be generated at this cycle, but no interrupt would be generated here. And then the fourth way is rising edge. So in that case, we would generate an interrupt at this point, but not at this point. And those modes are controlled by a register, and that register is called EICRA. So let's go to external interrupts and the register description. So external interrupt control register A. So 4 of the bits are reserved, so those are always 0. And then here we have 2 bits for each of the 2 external interrupts. So ISC11 and ISC10 control interrupt 1, and then ISC01 and ISC00 control the sense mode for interrupt 0. And this table shows you how to set up what values to give those bits depending on the mode you want it in. So if they're both zeros for interrupt 1, then it's low level interrupt. 0, 1 gives you an interrupt on any logical change. 1, 0 is an interrupt on a falling edge, etc. All right. And then the other interrupt would be the external interrupt mask register. And this just enables interrupts from these 2 sources. So if we write a 1 to this, then we are enabling interrupts from INT1. And if we write a 1 to the 0 bit, then we are enabling interrupts from INT0. All right, now we'll get into the example. And the camera's not working. Hopefully it'll come back. Please bear with me. Okay. So here for our example, we want to increment a counter variable. We're not really doing anything with it. We're just making some variable go up 2 times every second. But we want to reset the counter when either reach 100 or when a button is pressed. And that button is going to be connected to port D, pin 3. So here's a little drawing of our microcontroller. And port D, pin 3 is physical pin number 5. Port D, pin 3. And connected to that pin, we have a button that is going to pull that pin to ground whenever the button's pressed. So let's get to the code. So we're going to include io.h. We're going to include interrupt.h. And to get this delay for the counter, we'll just use underscore the delay ms function, just to keep things simple. And so we need to define FCPU as 8 million and include delay.h. All right. Now, this is going to be pretty new, and we'll talk about why we're going to do this next line at the end. So we want to declare a volatile, var variable, and we'll call it I. And it's defined, it's a global variable because we've declared it outside of any function. So now we'll go ahead and write main. Assign the value of 0 to I. Make port D inputs. Enable the internal pull-up resistor on port D pin 3, because without the internal pull-up resistor, whenever the button's not pressed, this would be at an unknown voltage. So the internal pull-up resistor will keep this pin at high voltage whenever the button's not pressed. And so enable internal pull-up. And now we can go ahead and set up our interrupts for that external interrupt. And we'll write to EICRA, external interrupt control register A, and we're going to give that a value hex 08. And this is to get an interrupt on falling edges on the INT1 pin. So let me go back. So we assigned it an 8. And so an 8 would be a 1 right here. And so that's 1, 0. So falling edge of INT1 generates an interrupt request. And we did that because INT1 is going to be high voltage all the time until the button is pressed. It's high voltage because we enabled the internal pull-up resistor. And so when the button is pressed, then that pin goes to ground. And so we want that falling edge to generate the interrupt. And next we need to enable the external interrupt. So external interrupt mask. And we'll write a 1 to bit 1. And now what comes next when using interrupts? We have to enable interrupts globally. So SEI. Now inside of our while loop, we're just going to handle that code with the counter. So we want the counter to count up to 99 and then go back to 0. So we'll use a for loop for I equals 0. And notice we didn't declare I here because I has already been declared. So instead of writing, int I equals 0, we just write I equals 0. So we start out our loop assigning I to be 0. So we don't need this line here because right here we assign a value to I. And as long as I is less than 100, we're going to execute the body of code in this for loop. And after every time we've executed the body of code, we're going to add 1 to I, so I++. And what do we do inside the for loop? Well, we just delay for half a second. So delay 500 milliseconds. And then after we've delayed, we add 1 to I, check to make sure it's still less than 100, and then delay again. So all we're doing here is counting up from 0 to 99, and we're adding 1 to the variable I every half a second. And that's all we're doing inside of this program. So it's really just an exercise because it has no physical ramifications. And now the other part of our problem description said that we want I to be reset whenever this button is pressed, or when it goes, up to 100. So it goes back to 0. When it goes 0 to 99, then back to 0, and then up to 99. But when a button gets pressed, we want I to go to 0. So we're coming to the ISR, and we're about to see why we declared I as global, and why it's a volatile int, or volatile variable. So ISR, and then the vector name is int1 vect, and we got that from the vector table in the data sheet. And all this does is sets I equal to 0. So the variable I has to be global because it's used in both of these functions. And if it wasn't an interrupt service routine, if it was just a function that we called, then it would be better off for us to pass it the variable value. So we would declare I inside of main, and then it would be a local variable. But since it's an interrupt and we don't know, we're not actually calling it out of main, then in order for that data to be shared between the two functions, it has to be a global variable. So that's why it's a global variable, but then why is it a volatile variable? Well, that's because, not necessarily in this case, but in some cases, a compiler could look at the code, and if there is no way that that variable is modified inside of main, so say it's just read inside of main, but it's modified inside of the interrupt service routine, then the compiler could optimize the code and just set it to be a constant value. So the result is that if you didn't have this volatile in the declaration, then in some programs you would get into the case where the compiler made that variable a constant inside of main. And so no matter what happened in the ISR, the variable inside of main would not change. So just to remember that whenever you use a global variable with an interrupt service routine, you need to declare it as a volatile variable. And that's the end of the video. So we've gone over 2 examples of using interrupts. One interrupt used the timer, and one interrupt used the external inputs.